So I want to go through another practice problem for determining empirical formula with a chemical compound. And in this case, we're going to replace oxygen with sulfur. So it's the same idea. We use the identity of carbon dioxide and water for determining how much carbon and hydrogen is in there. And then we subtract those grams from the total to determine how many grams of sulfur are there. And then remember, we do the whole percent to mass, mass to moles, divide by small, multiply until whole. So we have to get the percentage. So this is kind of the walkthrough in this problem. We have a sample that contains 13.660 grams. And we have the 19.352 grams of carbon dioxide and 11.882 grams of water. And remember, we're using this is what we do in a chemistry lab, where we would burn these compounds and then we would get the amount of carbon dioxide that came off and the amount of water that came off of that combustion reaction. So that is what the chemicals that are going to react that are released once we burn that initial sample. So this is the starting point, but the carbon dioxide, right, we're looking at the carbon in here, but that oxygen is also going to add to the weight. We're looking at the hydrogen here, but the oxygen also adds to that weight. So we have to take that into account. So first of all, we are going to look at this sample here. When we're doing this, the first thing we need to do is find the atomic and molecular masses. For carbon, it's 12.011 grams per mole. For hydrogen, it's 1.008 grams per mole. And for water, 18.015 grams per mole. Remember, we got this by adding 16 plus 2, that gives us the approximately 18. And then we have the 12.011 that we would see over here. And then we're going to add the 16 times 2, which would be 32, to get our 44.01 grams per mole. Remember, we just add up the atomic masses of all the atoms within that compound. So these are the molecular and atomic masses for these compounds. The next step now is to determine how much of these samples are made up of just carbon and just the hydrogen. And we're starting with the 19.352 grams of carbon dioxide. And that's the grams, but we have to, in order to get to an even amount, we have to go through molarity because these have different masses. So we need to turn these grams into moles first. And in order to do that, we use this molecular mass. And this is going to be 44.01 grams of CO2 per 1 mole of CO2. So the grams will cancel out of CO2, and then we'll be left with moles of CO2. So I'm going to calculate this. When I put this into my calculator, I get 0.440. And that is going to be my units, are moles of CO2. Now that's not quite what I want yet. I want to know how many grams of carbon. So now I need to use what I know about this compound to determine how many moles of carbon per moles of carbon dioxide. So if I have 1 mole of the carbon dioxide, and that's the group that I'm trying to cancel out, I know that I have 1 mole of CO2, carbon, in this compound. So for every 1 molecule of this, I have 1 molecule of carbon. For every 1 mole of this, I have 1 mole of carbon. So it's a 1-to-1 ratio. And then that'll allow me to cancel out my moles of CO2. I'm going to add another thing in here because I know my units will be moles of carbon at this point, but I want grams of carbon. I want to know how many grams of carbon are in that 19-gram sample of carbon dioxide. So then I go back to the atomic weight. I know that 1 mole of carbon is equivalent to 12.011 grams of carbon. So then I will solve for the grams of carbon, and if I multiply this in my calculator, I get about 5.2 grams of carbon. I'll do the same thing now for water. The only difference is this isn't a 1-to-1 ratio anymore. It's a 2 hydrogen per 1 molecule of water. And I'll start with the 11.882 grams of water. I need to use the 1 mole of water to determine the amount I have, 18.015 grams of water per 1 mole of water. So this is going to give me the molar amount of water rather than in grams. I'm going to just continue on so you avoid some rounding errors if you just kind of do this in one calculation rather than stopping and then typing in 0.440 times 12, for example, in the example above. So I'm going to just keep going. I know that I have my units currently are in moles of water. So the next step is I want to cancel out moles of water using the ratio of, so if I know I have 1 mole of H2O, I get 2 moles of hydrogen out of that because there are 2 in that compound. So now I'm in, my units are moles of hydrogen, and I can use the atomic mass of hydrogen for every 1 mole of hydrogen. I know that I have 1.008 grams of hydrogen, and then I'm going to use this whole equation to calculate out the grams of hydrogen from that original sample. When I do these calculations, I get 1.330 grams of hydrogen. So if I take that original, so I have my grams of hydrogen, I have my grams of carbon. If I take that original 13.660 grams of my sample, and I subtract out the 5.28, and actually had 1 grams of carbon in my original when I had this calculated, minus the 1.330 grams of hydrogen. Remember, this originally had carbon, hydrogen, and sulfur. So once we've determined the grams of hydrogen and carbon, then everything left over is the sulfur. And that's going to be the 7.049 grams of 49 grams of sulfur. Now I have this amount of sulfur, the amount of hydrogen, and the amount of carbon. So I'm going to erase all of the ink on the slide, so if you need to write any of this down, I would pause here. And I'm going to start kind of with a fresh page. My next step is to determine if I have the 5.281 grams of carbon, and I divide that by the whole sample and multiply by 100, that gives me 38.66% carbon. I'll take the 1.330 grams of hydrogen, divide that by the total, and multiply by 100, and I get 9.74% hydrogen. And then finally the 7.049 grams of sulfur divided by the 13.660 times 100, and then I will get the 51.60% sulfur. Remember, for empirical formula, we have to start with the percent to mass, so we need to determine the percentage first. So we can't skip that part, otherwise if you just go from mass to moles, right, if I take these and then determine the moles, the percentages won't add up. So I'll just get what was that in that original sample, but I'm not going to be able to use that to determine the empirical formula. So this percentage calculation, that's essential. And remember, this should equal approximately 100%. So now that these are approximately 100%, that means that out of 100 grams, right, that's kind of where we simplify this. We go from percent to mass. I'm going to say, well, now these are essentially grams, right? 38.66 grams of carbon, 9.74 grams of hydrogen, and 51.60 grams of sulfur. If I have a 100-gram sample, that's the number of grams I will have out. So we're going to do that to simplify everything so that we can now look at this through the number of moles we have, because moles allow us to make equal comparisons with the atoms within a compound. So that is the kind of unit we need to use. So we have grams of carbon, and I know from looking, right, so I don't have 12.01 grams per mole for carbon, 1.008 grams per mole for hydrogen, and then sulfur is going to be, looking up at the periodic table, 32.07 grams of sulfur per mole of sulfur. So we can use these grams percent to mass, now mass to moles, and we do that with the atomic masses. So I will multiply this by 1 mole of carbon over 12.01 grams of carbon, and this one is 1 mole of hydrogen over 1.008 grams of hydrogen, and this one here will do 1 mole of sulfur divided by 32.07 grams of sulfur. So these will give me my molarities, or the number of moles, and that will be 3.22 moles of carbon, 9.66 moles of hydrogen, and 1.61 moles of sulfur. Percent to mass, mass to moles, divide by small, and I will divide by the 1.61. And in this case, I'll get a 2, a 6, and a 1. And multiply till whole. I don't have to because they're all whole numbers currently. So that means these numbers are the number of atoms within our original sample for the empirical formula. So carbon, we have 2. Hydrogen, we have 6. And sulfur, we just have a 1. So that would be the final answer for the empirical formula for this problem.